The title of my talk is the world more or less and only as we see it? And what I'm going to present to you are some theorems on what I call invention of structure on the world by conscious agents, with a view to demonstrating that that's not the case. I'm also going to, in the process of doing this, I'm going to introduce the interface theory of perception and conscious realism, the author of which is sitting right here. And so in this talk, I will show that evolution by natural selection entails that physicalism is false. Okay, which is really funny because the next talk is going to be physicalist, but I think we may have something in common, actually, in spite of all that. First, I want to explain what physicalist theories are, in brief. The idea of physicalist theories is that perception is a reconstruction of an objective reality. Okay, so some of the assumptions that go into physicalism are that our perceptions estimate true properties of the physical world. Okay, the objective true properties, and that evolution guarantees that these estimates are accurate, veridical. So it follows that physical objects have causal powers. That's what I was taught right through college. And as a consequence, brain activity, which is a physical activity, causes consciousness. Okay, so what I want to do here is to question these assumptions. Here's the first one is perception actually veridical? And here's a color from motion. I think you came up with this, right, Don? Where these blue dots are crossing the screen, and it looks like there's a shadow, blue shadow in there, but it's not actually there. Okay, so this is just one example of a gazillion visual illusions that you can find in Don's book, for example. The other assumption is that natural selection favors veridical perceptions. There are lots of ways of questioning this, and I'll just put in a brief triple of slides to show you that there could be a serious problem in terms of veridicality. But there might be young people here, so I'm going to move on. So here's a quote from Steven Pinker in How the Mind Works, which I think is very telling. He says, "We are organisms, not angels, and our minds are organs, not pipelines to the truth. Our minds evolved by natural selection to solve problems that were life and death matters to our ancestors, not to commune with correctness." Okay, so one of the great people in the field feels this. So let's start by proposing an evolutionary theory of perception. Everybody agrees to that. Okay. So I'm going to present three theorems. Actually, I'm not going to talk very much about the third one because of time, but in the first theorem, I'm going to show how interface agents, a certain type of agent that is whose perceptions are not veridical, dominate under natural selection agents that are veridical, that do see the truth. Okay, in my second theorem, I'm going to demonstrate that conscious agents can impute a spatial structure on the world which the world itself may not actually have. All right, so the world may have a completely different structure from what we think we see of it. And it's perfectly okay by the world. And the third theorem is a similar theorem which says that conscious agents impute probabilistic structure to the world. Our estimates of what's going on, our best estimates of what's going on, the probabilistic structure of the world. But the world may not actually have that structure. In other words, for both these last two theorems, different species may impute different structures on the same world. Okay, which then makes me question whether that structure belongs to the world or does it somehow belong to at least the species and its interaction with the world. Okay, so very quickly, what is a physicalist evolutionary theory? This is a theory where it's assumed that our perceptions have evolved as veridical representations of the objective world. And so veridical perceptions we will define as those which are attuned to the structure of the world. Don Hoffman introduced the interface evolutionary theory, and this says that our perceptions have evolved, or we agree with evolution, but as a user interface between us and an objective world. Okay? So interface perceptions will be defined as those that are attuned to evolutionary fitness, not necessarily to objective realities. So here's a quick picture, which I also stole from him. Here's an object which has great fitness for one species, but zero fitness for another species. Though this picture is getting increasingly interesting because now this guy doesn't know, that's fresh meat. And there's negative fitness coming from this fellow to this guy. So anything can happen, is the story here. So we have, okay, we've covered sex and death, now we need music. The kinds of mathematical models that I'll be using, for those of you who are interested in what sort of math comes into this kind of research, will include evolutionary game theory, a well-established theory of replication, retention, and selection, which is considered to be ontologically neutral. It's not making any claims about what's actually going on in the world. Probability theory and Bayesian inference, again, very standard. It's a theory of inference from uncertain evidence. And finally, group theory and geometry, which is the standard approach to space, time, symmetry, and so forth. Okay? And these are pretty much the kinds of mathematics that go into almost any scientific endeavor. I'm going to discuss that first theorem about interface agents dominating truth agents. And for that, I need to set up the structure for this. So this is especially suited for those who are slightly mathematically inclined, but I'll try and go through it quickly. Okay, so how do we model these perceptual strategies? We're comparing two different perceptual strategies, the truth and the interface. And in order to do that, we assume that we have a set of world states, which we call W, and a set of perceptions called X. And an ideal perceptual strategy, then, is something that assigns a percept to each world state. So in mathematics, we call that a function that assigns to everything in W something in X, a unique thing in X. Okay? For those of you who are interested, this is a limited definition because there is dispersion in the real world of perception, and so we want to also allow for more general possibilities where this function P outputs probabilities. It gives you a probability distribution of possible perceptions for any given world state. Different people are going to see slightly different things, and there will be some uncertainty involved. So P is a Markovian kernel, but I'll act as if it's a function through the rest of the talk, most of the rest of the talk. Okay, so I think everybody agrees that world states give rise to perceptual states. What's fitness? Fitness is a very simple thing. Given a species, given its environment, given its sort of various classes of things of interest, it's at least species specific, and it assigns to each world state for this species a positive number called its fitness. Higher number, more fitness. So that's again a function on the world, but now it's a function into the real numbers, a positive real number, or maybe zero for that matter. Okay, so non-negative real numbers. So that's what fitness is. Now, we'll describe a veridical or truth strategy as a strategy. What we're doing over here is we're assuming that there is an objective world, and then I will show that that's sort of a contradiction in terms. Okay, so I'm saying, okay, if you say there is an objective world, let's assume there is one. And in that case, we can define a veridical strategy because there's an objective world. And what this thing does is it takes any percept, X, and looks at all the possible world states that could have given rise to this percept under that map P that I mentioned before, the perception map. And it uses Bayes' theorem to estimate the most likely such world state, which we'll call W sub X, most likely state. And then for each X, you'll have a most likely world state. That world state will have a fitness. And if you consider all these X's and all the corresponding world states that have been computed using Bayes' theorem, you look at the one with the highest fitness. Choose that percept X naught that maximizes the fitness of its maximum a posteriori state. So the best possible thing you could do in terms of all the realistic world states that could have given rise to your percepts. Okay? So it's like really maximizing everything as best as you can do, but sticking to the truth. That's the idea. Okay? So this is a fancy formula that says exactly what I just said. Okay, so don't worry about the formulas. So if you think of the world as this fat region here, and the flat region here is your perceptual space, then your perceptual map it takes world states to percepts, and given one percept X, the fiber above it, which I call P inverse X, is the set of all world states that could have given rise to it. One of those will be chosen as the maximum a posteriori world state, okay? So to complete this, the fitness of the percept X is the average of all the world states that could have given rise to it, okay? So the previous slide, we were picking a world state, but now, if we just think about the percept X, what is the fitness of this X? Well, I'm going to define it as the average of the fitness of all these guys. And the interesting thing is that that also uses Bayes' theorem to compute. So we're using Bayes' theorem for both veridical as well as for interface strategies, because the interface strategies use this concept. And that's coming up in the next slide. We're almost done with the hardcore math development. The interface strategies, what do? Well, first they compute the average fitness that I just mentioned on the previous slide for each percept, okay, of this perceptual map P, which is considered given, and then they choose the percept that maximizes the average fitness of its fiber. So, you know, if an organism is looking for a resource, if it's a veridical organism or truth-based organism, it's going to do the first strategy and look at that region which maximizes the maximum a posteriori, blah, blah, blah. Whereas if it's an interface organism, it will choose this strategy to find the region where it should start eating its food or its resource. So it's a particular model. Okay, so which strategy dominates? Well, there's a well-established theory called evolutionary game theory, and it has various theorems that can be applied over here. And when we apply them, we see that with a given world and a finite sensorium, a finite perceptual space X, which for most of us is true, we have finite perceptual spaces as far as we can tell, given that there is an objective world. Okay, then over all possible fitness functions and all a priori measures that exist on the world, a priori situations in the world is the way to say that, then the probability that an interface perceptual strategy will dominate a veridical strategy is at least this number, where that bar X bar is the size of the perceptual space. So as the size of the perceptual space increases, the size minus 3 divided by the size minus 1 goes to 1. The probability goes to 1. So there's actually a specific estimate over here. The upshot of this really is the following. The upshot is that as the size of the sensorium increases to infinity or gets large, the probability with which interface strategies will dominate veridical strategies goes to 1 generically in the situation. So what does that mean? It means that we have evolved to match fitness, not necessarily to match an objective world. So what we're looking at, what we think we see, is determined by our evolutionary fitness requirements, not by some objective reality. Kind of irritating, you know, until you get used to it. Okay, so the implication then is that our physical vocabulary that we're using is an extension of our perceptual predicate vocabulary, and therefore is the wrong vocabulary for the causal structure of the real world. It's not appropriate for the real world. It's eminently appropriate for us until we run into trouble, of course, which we often do, and that's how we evolve. Okay, so there are various objections to this. Don't fitness functions correspond to the truth? I mean, aren't they homomorphic to an objective structure of the world? That's what most people would say, and you know, we all believe it. At least intrinsically, we believe that what we're seeing is what we're getting. But a little bit of, you know, a study of what would happen if we were to impose any kind of structural conditions, the mildest structural conditions on the world, the topological, metric, various kinds of conditions that come into play in physics or in perceptual and science and so forth. It turns out that the probability is 0 that this would happen. And in any case, fitness is a species-specific thing, so which species are you talking about when you ask that question? Here's a quote from Bertrand Russell. I just put it up there because it's nice to quote Bertrand Russell. Nobody ever does these days. Um, and he said, thus it would seem that wherever we infer from perceptions, it is only structure that we can validly infer. The question, though, I think is absolutely right, but what structure? Is that structure in the world, which is, of course, what I think he meant, or is it in our perceptual apparatus? Is it in our perceptions? Not even apparatus. The apparatus itself is in the world of our perceptions. Okay? There's another objection to the domination theorem. We all agree on, well, there's a consistent agreement on things like 3D shapes, textures, smells, tastes, all that stuff. We all seem to agree on a lot of it, actually. And that's a very, very strong intuition. And the next theorem will show that these intuitions are dead false. Okay, so I really like that way it dropped down. So in brief, the theorem that's coming later is going to say that an agent can see space as a property of the world, whether the world actually has that structure or not. Okay, so we impute structure onto space ourselves in some way. I mean, space has to be amenable to it. It has to say, okay, I'll let you do that, and all the other 5 million other species on the planet can do their own thing too, effectively. Okay, so that leads us to propose the interface theory of perception. In the interface theory, the idea is that space-time is like our desktop. It's an interface. You notice that before I had these pictures look like a computer screen, and that was entirely intentional. In fact, it was Don's computer screen too. So the idea is that space-time, as we normally know it, it's our desktop. Physical objects, what we call physical objects, are icons on this desktop. And their interactions is physics. So icons seem to interact via physical law, all right? And the reason I say seem to is that it's our perceptual interface where this is all happening, and therefore physical causality by itself is a fiction. There is causality, perhaps, but it's not necessarily the way we see it. Okay. So you might say, as people did ask Don before his TED Talk, why don't you just step in front of a train? It's just an icon. But the point is that we take our icons literally. Famous example being, you don't take your thesis and drag it to the trash. What's actually happening is a bunch of things that are happening inside the hardware, which are going somewhere else in the hardware, and then they're just, turning into heat. But what you see is your thesis and the trash, and you don't do that. Unless, of course, I think there's a movie later on tonight about a brilliant mathematician, was it tomorrow night, who decided to quit mathematics and go into the universe. I haven't had that courage myself, but so for him it would be okay. So the question arises, if evolution favors interfaces as perceptual strategies, and if space-time is a species-dependent construction, then this invites us to start anew in developing a model of consciousness. It seems reasonable, because now we're not quite sure of what we're up to. So, a conscious agent, we'll all agree, interacts with its world. Actually, I did meet a Russian mathematician in Belgium 2 weeks ago who said, there is no world. It's obvious, there's no world. I didn't know what to say to him, but he may be right, but I think as a working hypothesis, we'll imagine that there is a world. And that an agent is interacting with it. So let's try to define clearly what is meant by an agent. So here's our definition of a conscious agent. Conscious agents have experiences, and these experiences lead to actions on a world from which we are having these experiences and performing actions on. And so we're going to just call them W, X, and G. X for experiences, and G for go and do something, right? For mathematicians, G is a group, but anyway. And then we're going to call P, as I mentioned before, the perceptual map. D is a decision. Based on the experience one has, you make a decision to act. And you choose a particular action. And then that action acts on the world via a map A. So these maps are all acting along this triangle. And then there's a counter, N, which just counts how many experiences you've had up to this point. Okay? So we'll call that a conscious agent. It's a 7-tuple. Okay? Deeper analysis suggests that these things are actually probability spaces. We want to be able to include the possibility of uncertainty in our perceptions and actions, okay, and our decisions also. I can't be quite sure what decision you're going to make, whether you're going to dribble left or dribble right with the football, but you know I can have an idea of what probabilities are, okay. So and n of course is just some integer, and then these mappings between the spaces W, X, and G now become Markovian kernels. Basically functions which are a little fuzzy. Think of them that way, and ignore what I'm going to be. If you're not mathematically inclined, ignore this. But if you are, please look at it. So we're basically saying that each of these functions depends not only on the current, say for example, the P, the perception depends not only on the current world state, but also on the previous perception. The previous perception can influence the current perception along with the current world state. So this is the most general conceivable model of a conscious agent that we have, keeping the minimal amount of assumptions. That's our proposal. And it's falsifiable, of course. So it's still a 7-tuple, but it's got a richer structure than I mentioned in the previous page. Okay, so the conscious agent thesis then is that every conscious entity and its activity can be modeled by conscious agents, and that's a falsifiable statement. But we're going to accept that, and then we're going to see if we can develop a theory of experience through this. Okay, so that allows me to now tell you a little bit about the second theorem, which is the invention of space. Space, or space-time, is essentially it's a set of points. It's a set, okay? In mathematics and in physics, we consider a space or a space-time to be a set together with a group of symmetries that act on it. Okay, so the symmetries are an essential part of all the spaces that are used in physics. Okay, so for example, the standard geometry that we did in high school is based on the space of, say, R2, the plane, and the group of symmetries is the Euclidean group where you can move congruent triangles into congruent triangles. So they preserve certain structures. That's the symmetry. And that preservation of structure is under a collection of actions that form what mathematically is called a group. Okay, so there's a standard definition. I'm saying that any space has these two essential elements, okay? And different spaces will have different elements and different actions and so forth. So, colloquially, here's the statement of the second theorem, which I'm going to state in gory detail in the next page. But if a conscious agent's actions form a group, which is a specific mathematical object that describes symmetries of space, and if the agent's perceptions are tuned to its actions, which I'll explain on the next page, the agent will see the geometrical space for that group in the world. It'll imagine that the world has that spatial structure, okay? And the world may not have that spatial structure, okay? What do I mean by tuned to its actions? Well, basically, it really means that this group G acts on its perception space in a certain way, so that when the agent acts on the world and then the agent perceives what happened, regardless of what actually happened in the world, X it means that these two mappings behave nicely with each other, so that in some sense you can ignore the actual structure of the world, if there is any. That's what attuned means. And I'm going to give you for the sake of the mathematicians here, I have to give you an accurate statement, so bear with me. That's coming next. Okay. So suppose that a conscious agent's action space has the structure of a group and is a symmetry group for the agent's perceptual space. So it's got this nice internal thing, you know, it likes itself. And we'll write the action as G dot X. Then G acts on the world, But the way in which it acts on the world need not be a symmetry action. It may not have any symmetries on the world. It's not a group action, okay? But even then, if the perceptual channel P and the action channel A are attuned, that means for the current percept X, we have for the next percept X prime, that it's related to the action and the old percept this way. So you see how P and A have to behave nicely with each other. Then, the perception action experiences of this observer will admit G as a group of symmetries on the world W. Okay, it's actually the fibers, because all you can see is the fibers anyway. The observer sees a spatial structure in the world given by the symmetry group G, but it is the agent that has this structure. The world may not have this structure. Okay. So there's also agents invent probabilistic structure. This is just too gory for words. I'm going to move on. So the traditional mind-body problem is that the physical world gives rise to consciousness, and the physical world is fundamental. What we're now proposing is a reverse mind-body problem, which is equally hard, by the way. How does consciousness give rise to the physical world? Let's assume, at least, now that we've run into all these problems, and now that neuroscientists have found tons of neural correlates but never causation, let's think a little bit about how we could maybe go the other way, okay? So the conscious realism thesis is consciousness all the way down. Conscious agents all the way down. The world consists of conscious agents communicating with each other. Again, a falsifiable thesis, and that's where our research is now proceeding, okay? Very quickly, where do we go from here? Well, there are various questions you can ask. One is, how do conscious agents combine statically or dynamically to produce new conscious agents? We're imagining this incredible combinatorial explosion of conscious agents communicating with each other, and then maybe periodically or for a short period of time identifying as new higher level conscious agents interacting with each other. This goes on forever. And the other idea, which is to build circuits of conscious agents and explore their properties, including things like standard questions in perception science, like memory, predictive coding, etc. And we've just Chris Fields, who just walked in a little bit a while back, was the lead author on a paper which has just been accepted. Congratulations. And on that subject. And we also want to be able to show how space-time, how does space-time emerge? How does our space-time emerge as an efficient coding scheme from the interaction of conscious agents so that we eventually use it as an interface? That's really the burning question. How do these interfaces come about evolutionarily? And so we've been working on how you can compress the information space, what was happening in that whole triangle, okay, using geometric ideas, using geometric algebra, to compress it in such a way that we can actually do something with it. And the reason why we actually need to do something with it is pretty evident in this picture. What we've done over here is plotted the amount of things in information space up here versus the geometric compression, the dimension of the geometric compression space, it being 2. We're just coming down to a 2-dimensional vector space to compress all our information. And you can see that even that when there are 4 bits of information in each of the basic spaces, there's just 5 pieces in information space. But when there are 5 bits, there are 63,701. So there's a massive combinatorial explosion of information as the number of bits in your space go up, which of course they have to go up. I mean, we have to have a rich perceptual experience. But as it gets richer and richer, the need for compression becomes incredibly urgent. Okay, here's another picture that shows this for n equals 3. If I decide to go to a slightly richer compression space where I'm looking at things through a 3-dimensional lens, which is familiar to us, then you can see that when you get to, say, even 4 bits in each of our perceptual spaces, you're compressing a billion trillion pieces of information into what you can actually see, so that you can make sense of it. Okay, so this is some mathematical work which is supporting the ideas of conscious agents. The larger question for the future is, how does physics arise from consciousness? Is quantum theory in some sense natural? It seems increasingly so. There are lots of talks on how quantum theory is much more representative of our inner reality than of course, classical physics is. And it may be very natural as emergent from conscious agent dynamics. So we looked at circuits of just two agents, and we actually saw quantum behavior emerging in an asymptotic limit. It's very interesting and intriguing. We're not claiming that this is a result yet, but it's something worth pursuing. Okay. Another question is physical law immutable? Does it exist forever, or is it something, considering it's on our interfaces, this is a worthwhile question to ask. Okay. Does consciousness evolve? And if it evolves, does physical law evolve? Maybe, okay? And then there's a big question. The biggest question of all, I think, is what drives the evolution of consciousness? Now, Federico Fagin will be talking with Edward Frenkel tomorrow, and you know, I love his ideas about this. What drives the evolution of consciousness? And I'm just going to leave you with a very provocative, the mystery part. That's the third thing that's meant to be in a good novel, right? Okay, so a provocative thought of his, which is that it's the urge for consciousness to know itself, the pleasure of the aha that continuously builds on itself and which creates the universe. So that tells me that I'm done. Okay, so thank you.